Douglas, can see the slide?
Yes. Yes.
Okay, thanks. Okay, so let's continue today. Okay, so far we learned about just senses. Okay, meanwhile I sent the practical question for this week. Okay, the WhatsApp. Yeah, try to have a copy. You don't print out also can. Just try to have a copy along with you. Okay, so far we learned about operation amplifier. We learned about the sensors. We learned about how many senses? We learned about 4 senses. Sensing device done. We are doing the second one now. Okay, so sensing device, processing unit, output device. Remember the 3 department. So these 4 senses. Light dependent resistance what? Light greater, temperature. When light intensity higher, resistance smaller, so less voltage. Okay, thermistor temperature high, resistance small, less voltage. Transducer pressure high, voltage is high. Strain gauge, strain high, resistance is high. Okay, strain gauge, as I said, used to check cracks in the bridge and everything. Okay, so we done this. Then we talk about operation amplifier. It follows a formula. So these are the 5 properties you must know until 3 properties. Okay, ideal op amp. There's a 0 impedance input. Input is infinite impedance. 0 output impedance. Infinite open loop gain. Gain is infinite. Bandwidth is infinite. That means any frequency it can produce, it can work at its optimum level. Okay, if it said gain 50 means it always keep gain 50. With bandwidth is infinite. So then slew rate, no delay in the processing. Okay. Okay, so we talk about this is the formula it follows. That day we follow up to here. Up to here, yeah. So we talk about LDR. So how LDR can on the street light. Okay. Okay, now I'm going to add more questions. Okay, look at this. This LDR, this is used for street light. Street light. So because here up R, down R, as I said, what? If here up is positive 10 volt, down is 0 volt, RR potential difference, each will take 5 volt. So the voltage going to the negative is the lower resistance voltage. So down is 5, so the input voltage is 5 volt. Okay. The second one, F and LDR. LDR will control the input at positive. So when the light intensity is high, resistance of the LDR drop, so voltage input V positive will drop. So V positive greater than V negative, output will be positive, so it works. Okay, now I'm going to add you a question. I'm going to ask you a question. The question is, let's say you want to convert this to, used to ask this before. Let's say they want to use this for the fire alarm. Okay, they want to use this system for a fire alarm. Fire alarm. Fire alarm. You want to put this circuit into your room so that it acts as a fire alarm. So the output will be alarm. So what type of sensors do you use? What sensor are you going to add in? You need to add thermistor, right?
Yes.
You need to add thermistor. So thermistor, I want to add between the 1 and 2. Now the question is, where do you put thermistor? Do you put that thermistor to replace the 1 or replace the 2? 1 minute for you to think. One or two. So you think two. Okay. So you must put thermistor in such a way that the output to become positive or negative when temperature high.
Positive.
Positive. Okay. So let's say we put a thermistor at 2. We put a thermistor at 2. thermostat 2. So when temperature rise, what happened? The resistance of the thermistor become small. So the voltage across thermistor will become small. So the V negative become small, right?
Yes.
V negative becomes small, right?
Yes.
So when V negative becomes small, yes, according to the formula, it become more positive, right? Right, good, very good. So the A equals to V plus minus V negative. So the thermistor need to put at 2 so that when temperature rise, resistance drop, voltage V negative drops. When V negative drops, it most likely to become positive. Yes, good. Okay, good. So thermistor must be at 2. Now think about the position of LDR.
But
LDR is you when the light maybe in the night time suddenly fire started in one corner, so the light going to reach first the sensor, then the temperature. So when the light detected, you want to on the alarm. So do you think the location of LDR is good?
teacher,
Yeah.
for the thermistor one, right? Isn't the thermistor need to put at the number one there? Because when the temperature increases, then the voltage the resistance decreases, then the voltage will become higher, and then the
Voltage
voltage
becomes
at
smaller,
the
right?
second resistor will become lower, and then this one will cause the output to be positive, right? And then because the higher temperature will cause the alarm to sound.
What?
So you see, so if the temperature get high, resistance go low, right?
Yes.
Resistance go low, voltage get low,
Voltage
right?
will get higher, right?
Low resistance use low voltage. Potential divider method. Potential divider method. Low resistance will use less voltage, right?
Oh yes. Then doesn't that means that the voltage in entering the negative supply will become smaller, and then this
Yes.
one will cause. Oh,
So,
okay.
good idea. So V negative smaller lah. So V negative smaller, it become chances to become positive is higher. Okay. So thermistor is correct lah. To position 2. LDR is it correct? LDR when there is a light, we want it to become positive. You put LDR at 1 on top, 1 or 2. Is it below is fine. And temperature when the light intensity rises, more fire, so resistance of the LDR drop down, voltage of the LDR drop, right? So then V positive becomes smaller, right? So is it good to place the LDR at 2?
Yes.
It should be at 1, right?
What?
Hold on, just give me a think about it. Hold on. Just give me a minute. Okay, so 1 or 2. Anybody? Should be here, right? Replacing the F, right? So LDR must be on top, right?
Why?
Yeah, it should be a fixed resistor. Agree?
Wait.
Agree, yeah? Okay, so this is how you manipulate the senses so that why you fix this resistor and what type of outcome you want. Okay, so next time they'll ask you to feel where do you feel the what do you call thermistor? I mean the senses. Huh? Okay, now let's say this original one, the technician made a mistake. He placed the LDR on top. You want to put it as a street light bulb as a street light. Okay, the sensors for the street light. We
Okay.
put the LDR on top. Top is LDR.
Yes.
Down is fixed resistor. What will happen to the circuit? What type of problem you're going to face? The light going to light up in the morning or in the night? Because LDR on top.
Morning.
So it will end up light up in the morning. So small changes the location of LDR. It will be output will be positive in the different day, because LDR when light and temperature when the light intensity rises, resistance drop, so voltage across LDR drop. But because LDR is on top, voltage LDR drop, voltage input at positive become big, because voltage input at positive is equal to the voltage used by the lower resistor. LDR on top. LDR voltage drop means lower resistor voltage become high, because both adapt voltage is constant. Last time I told you like 10 volt, like constant. Okay, good. So yeah, this is how the circuit looks like. Okay, this description is the one I told you just now. When LDR greater than F, so output is positive. Okay, in exam, it could be a 3 marks question they asked to explain. Okay, they asked to explain. Yeah.
The positive input is on the right vertical resistors, is it?
The input positive, the positive input is by the LDR.
By the LDR.
LDR potential, LDR and F potential divider. Okay. The negative input is by the RR, the bottom R, the bottom R voltage is the V negative. The bottom R voltage is the V negative.
Oh, okay.
In exam, they will ask you, we go back to the original circuit. They will ask you, okay, when light intensity is high, what happened to the output? 3 marks. So what you can write? You can write like this. You see here, when when light intensity high, resistance drop. The second line, when the LDR resistance of LDR is smaller than F, the LDR daylight, then V positive is LDR resistance is smaller than F, then the LDR is in daylight, then V positive will be smaller than V negative, and output is negative. There is a mistake here. When LDR is small, when LDR resistance is small, the voltage across LDR becomes smaller. So V positive, correct. V positive will be smaller than V negative, so output will be negative. This is how you should write. Okay, so V positive smaller than V negative, 1 mark. So output is negative, 1 mark, like that. But you have to tell when temperature rises, resistance decreases. So V positive smaller than V negative, output negative. You need to give answer in terms of the inequality signs. Inequality signs. Okay. So the function of the LDR here is act as a sensor. The function of operational amplifier is act as a comparator. That's a special name. Called what? Comparator. He compare the input. Okay, he compare the two input. Which input greater, he make the output same as the greater input. If positive greater than negative, the output will be positive. It's just comparing. Okay. Yes. So for example, V1, V2, input was positive 9, negative 9, output. If V1 greater than V2, V1 greater than V2, so what will happen? V1 greater than V2, output will be negative. Okay, so when V1 greater than V2, V negative greater than V positive, therefore V out is negative. So V out will be negative 9, equal to negative 9. Okay, because op-amp always will saturate. Either go to negative 9 or go to positive 9. We just now discussed earlier. It always saturate to the positive 9 or negative 9. It can't give very intermediate value, because normally it's easy to saturate. Why easy to saturate? Anyone? Why the op-amp easy to saturate? Because it has a very huge gain. It has a very huge gain. So easy becomes saturated. So when V2 greater than V1, output will be positive 9. Saturated to positive 9. You must use the word saturated. Okay, so another one example. You see the circuit. 2 op-amp given. These 3 resistance act as a potential divider. This is the input voltage. Input is given at the positive here and the positive here. Two positive input here. Okay. And now you have the output circuit is connected. Output circuit is two LEDs there. LED is there. Okay. Okay. Now let's say the input is positive 2. Input is positive 2. So input here is positive 2. If input is positive 2, look at the first op-amp. Negative how much? Negative is 5 volt. Positive how much? 2 volt. Output will be positive or negative? Positive, negative greater than positive. So output will be negative, right? Here will be negative. So tell me, green will light up or not? The green LED will light up or not? Green only light up when current is flowing from high potential to low potential. The output here negative. Up there is negative volt. Okay. Down here earth is 0 volt. Current will flow from negative to 0 volt or 0 volt to negative. Current will flow from high potential to low potential, right? So current will flow 0 volt to negative. But can current flow? Can current flow through the green diode? Cannot, right? Because you see the diode is forward bias or reverse bias at that moment. So the green diode is reverse bias because down is high voltage. So current cannot flow. So green will light up or not? Green won't light up. Okay, it won't light up. So when positive 2 volt of input, green won't light up. Why green won't light up? Because green LED was reverse bias. It's reverse bias because output is negative in the op-amp. Any questions about green? Then the same positive 2 go to the next op-amp here. This is also 2 volt. But the input here is positive 3. 3 versus 2. Who's the winner? Still negative is the winner. What? Negative 3. So output is negative. So red also won't light up. When B in is positive 2 volt, red and green both won't light up. Okay, both are reverse bias. Okay. Okay, now the input become positive 4. When input become positive 4. Okay, input is positive 4. What will happen? You see, now the input is positive 4. What happened? Here, up here 5. Down here 4. So who's the winner? Oh, still negative. Still negative. So green still never light up. But the positive 4 here for the second op-amp is 4 for positive input, non-inverting input. Negative was 3 volt. So here the positive greater than negative. So here output will be positive. Positive. So yes, red now will allow the current to flow. Red will light up. Red will light up. When positive 4 volt, red will light up. Green won't light up. Okay. When you give 6 volt, both going to be positive. So both going to light up. Okay. Yeah, this is like what do you call circular. Maybe checking the level of heatness maybe from a room surface. Maybe positive 4 means maybe the heat in the room is slightly higher. When positive 6 means when the green means when the red started, we said the heat of the room is slightly higher. When positive 6 means when both light up, maybe we can indicate that the temperature getting even higher or something as a detector. Yeah, as a detector. So the input must be from a sensor. If you check temperature, then you need to have input must be what do you call thermistor connected to another resistor in a potential divider method. Okay. Okay. Any questions from here? No questions. Whenever diode is there, you must use the term reverse bias, forward bias to explain whether they're going to work or doesn't work. Okay. Okay, so that is the comparator. This we 1/3 of the thing comparator. Okay, do you want it to saturate or not? Is it good for the op amp to saturate or not for this case? Let's say negative greater than positive, it become positive 9. Sorry, if positive greater than negative, it become positive 9. If negative greater than positive, it become negative 9. Is it good or bad to saturate?
Good.
Okay. Good, right? Because positive 9 means confirm on the
Oh, yeah.
alarm. Negative 9 means confirm don't on the alarm, right? If it never saturated, if like a positive 3, something like intermediate value, difficult to on the on or off the alarm. Because the op amp act as what? As a comparator, act as a switch. So switch means either on or off. That means either positive or negatively saturated. So it's good to be saturated, right? Right? It's good to be saturated, switching system. But sometimes, can we use this comparator circuit for amplifying a sound, music? Okay, opera singer is singing. Okay, can we the microphone is connected to what do you call another resistor here? Okay, so microphone is connected in a potential divider method. Okay, to the op amp. Okay, we have another resistor here. Okay, yeah, like this. Okay, so microphone. What is the function of microphone? Changing sound to electrical signals. Voltage will be created. There will be a voltage will be created. This voltage will go to as a positive voltage here. Okay. The opera singer said, let's say he said hello, what? Hello. This is how the analog signal. Okay. But when this signal enter into the op amp, how the signal going to turn to become? Let's say negative. How the signal going to become? All the positive is all the value here. Maybe the voltage may be like 2 volt, 0 to 2 volt. The voltage is changing. But here, the op amp going to do what? The entire curve here, the op amp, let's say, has an input of positive 9 volt, negative 9 volt. The entire positive here, the op amp going to saturate to what? Going to saturate to positive 9 volt. Assuming the negative is very low. Positive 9 volt. All the negative down here, you're going to saturate to negative 9 volt. So the op amp going to what? You're going to saturate all the input. No value in between. Just either positive 9 or negative 9. So the opera singer, which has the pattern of singing hello, whatever, this pattern cannot be retained. It's going to be saturated. This is good or bad for the music? This is not good, right? You want to amplify a sound means you need to retain the pattern or you don't want to retain the pattern. You need to retain the pattern, right? If the pattern is like this, amplification means this pattern we want to amplify it further, make the amplitude bigger without altering the frequency. That's amplifier, right? For the music. Okay. So for the case of music where the pattern need to be retained, we can't use comparator. Comparator doesn't work for music industry because it never retain the pattern. It saturate the values. Okay. For example, heartbeat. Okay. Heartbeat. Heartbeat also they put some sort of what you call sensor connected to the operational amplifier. Sense, of course, laptop the heart signal. Okay, this signal is very small from the sensor, but when operation amplifier amplify, if it's a comparator, the graph is going to produce in the CRO like a square wave. It will saturate. Do you want that for heartbeat? Can comparator use for the heartbeat to in hospitals? Also, cannot. So anywhere you want to amplify a signal, but you want to retain the pattern of the signal, you can't use comparator. You can't use comparator. So why you can't use comparator? Because comparator has huge what? Anyone? Why can't use comparator? Why comparator easily saturate? Because comparator has a huge what? Huge gain. There's a very huge gain. Okay. So what we can do? So they said we can sustain, we can maintain this pattern. We can maintain this pattern at the same time we can amplify it by reducing this gain. They say if we can reduce the gain, maybe this pattern can be retained. Okay, so how to reduce the gain? They said, okay, use another type, the second version of comparator called by doing feedback. It's called doing feedback. Okay, this is what they do. They do a feedback. Okay, feedback means what is feedback? Output voltage is channeled back into the input. It's channeled back into the input, and that then the partly will react to the input. And what happened? Finally, they found that the gain is dropping. Okay, so what is feedback first? The process taking some or all of the output amplifier, adding it to the input, known as feedback. It's called feedback. Okay, feedback. So they found that V out equals to A naught plus times input to amplifier. Input to amplifier is the original input plus fraction beta, fraction of output is added. Okay, so when they rearrange this formula, gain is what? Output over input. They found that gain is decreasing. Gain is decreasing. The A naught beta, 1 minus A naught beta, the number down here get what do you call? Get more than 1, so the gain will drop. Gain will drop. The overall voltage gain of the amplifier feedback is then given by this. So the gain is found to be decreasing. Okay, A naught decreasing. Okay. So last time V out over V in is perfectly A naught. Okay. Now down there you have a number now. You have a number, so the gain you have not 1 anymore down. So the gain become smaller. Okay, gain becomes smaller. So according to electronic, they say by doing a feedback, gain drops. Okay, the type of feedback famous in electronic is called negative feedback. Okay, negative feedback. What is negative feedback? Same definition. A part or all the output channel back into the negative input. It's called negative feedback. Okay, negative feedback. We put the connection to the negative feedback. Okay, if the fraction of beta is negative, denominator is greater than unity, the overall gain smaller. This is explaining when the beta is negative, denominator is greater than the numerator, so overall gain smaller than the open loop gain. And beta become negative. Okay, beta is negative. So normally negative lah. You see the input you give positive 5. Okay, output definitely going to be negative. Let's say negative. Okay, negative included here. So here become the beta itself become negative. So negative become plus. Denominator become more than 1. So the gain drops. Okay, the gain drops. So to be easier, just remember by doing feedback, gain decreases. Gain of the op amp decreases. Okay, the overall gain is smaller. This can be achieved by feeding back part of the output to the inverting input. Yeah, inverting input. If you put in an inverting input, this can be done. Okay. Okay, why do you feedback? Why you need to do feedback? By doing feedback, 3 benefit has been gained. 3 benefits. In exam, they will ask, what is the purpose of doing feedback? What do you get by doing feedback? The first benefit is increase in the range of frequency over which the gain is constant. Okay. This is something new. Bandwidth is increased. Bandwidth is increased. Okay. To understand this, I need to draw one graph here. See, I draw one graph. There is one graph missing in this slide. The graph is gain versus frequency. Gain versus frequency. Okay. The gain versus frequency for operational amplifier is like this. This is the graph. Flat line and line go to 0. Okay. Okay. This normally 10 to the power of 5 and 10 to the power of 5. What is bandwidth means? What I told you about bandwidth? What is bandwidth? Bandwidth is the range of frequency where the gain become constant. That is bandwidth. So for this op amp, where the gain become constant, this region, right? This region, right? The flat region. If you come down, the frequency F1, 0 to F1, 0 to F1, this is called bandwidth. This is the bandwidth of the op amp. Okay. Okay, now this is the bandwidth and the gain is 10 to the power of 5. Okay. Now by doing feedback, gain maybe drop to 100, let's say gain drop to 100. So now a new flat line will happen. This is the new flat line will happen, and then it continue here. So what happened to the new bandwidth? The flat line where the gain is constant. The new bandwidth increases. Okay. What is bandwidth? A range of frequency where the gain is constant. So lower the gain, greater the bandwidth. So that's the first benefit. Okay, benefit is what? Be able to increase the bandwidth. Okay, when bandwidth is greater, we said the op amp is more reliable because it has a greater bandwidth. Any frequency you input, you're going to amplify it to the gain set in the operational amplifier. Okay, let's say the op amp said the gain is 100, bandwidth is huge, you'll be happy because the opera singer give any type of frequency also, the sound will be amplified 100 times. Okay, yes, so that's the first benefit. What is the benefit of doing feedback? First benefit is increased bandwidth. Okay, bandwidth increased. Okay, next, therefore less distortion. Second, second benefit, less distortion. What is the meaning of less distortion? Just now I told you, right? If bandwidth is small, means let's say the bandwidth is only 10,000 hertz, only 10,000 hertz. 10,000 hertz is the bandwidth. The opera singer suddenly go for 12,000. Suddenly went to 12,000 hertz, the frequency she produced. So what happened? The gain, which is 100, normally it was 100, very loud. In the hall, everyone listening, she's singing 100. Suddenly she raised the pitch to 12,000. What happened? The gain dropped to maybe 50. Suddenly, the loudness becomes only 50 times. So this is distortion. Distortion means, I think the people who are in the hall will suddenly, the loudness become lesser because the frequency she made out of the bandwidth. So this is called distortion. Less causes distortion. Distortion means the signal was not amplified at optimum, at a constant rate. So less distortion. So distortion happens very frequently when the bandwidth is small. Small bandwidth gives lots of distortion. If bandwidth is big, less distortion. Okay, less distortion. Okay, so that's the second benefit. Okay, the third benefit is, of course, greater stability, more stable, and the system more stable. We call it more stable overall. So, what is the benefit of doing feedback? Increased bandwidth, less distortion, more stability. Okay. The only problem we have is what? These three has been achieved by dropping the gain. Dropping the gain. We can't have 10 to the power of 5. We can have maybe 100. I mean, the amplifier used in the hall, we maybe 100. The loudness increased by 100 times. Cannot go for 10 to the power of 5. More lower the gain, you said, more better, bandwidth get bigger, less distortion, more stable. Okay, why you need to reduce the gain? So that you get these three what you call benefit. At the same time, the input pattern can be retained. Okay, the input pattern can be retained. Okay, so this is feedback. Okay, so what is feedback? A fraction of output channel back into the input. By doing feedback, gain found to be smaller. By having lower gain, what happened? Bandwidth increases, less distortion, more stability to the circuit. Okay, where do you want to do feedback? When you want to retain the pattern. Okay, don't do feedback for alarm system, street light. We never do feedback. Street light, alarm system, we want it to be saturated. So we never do feedback. We want a gain to be very high. Either become positive or negative only, like on off. But to maintain pattern, you must do feedback. Any questions from this slide? No questions. Okay, something very new for you. Okay. So now, because of doing feedback, a new amplifier is invented. The amplifier called inverting amplifier is invented. Okay. The earlier amplifier we call what? Is a comparator. The earlier amplifier is these all are comparator. How do you know it's a comparator? No feedback. No wire is extended to the backward. If no wire extended to the backward, no feedback, it's act as a comparator. Okay. Now this one is the inverting amplifier. Inverting amplifier have two features. You have feedback. This is a feedback. You see the output. There is a wire connected backward. It's called feedback. This feedback is negative feedback. Why negative feedback? You see the output is connected to the negative input. So it's a negative feedback. Negative feedback. So inverting amplifier will have two features. One, it will have a feedback. Another one, the input, right? The input will be at the negative input. Will be at the negative input. The positive will be earthed. The positive will be earthed. Okay. That means what I'm trying to say in the formula. What is the amplifier formula? Output equals to what? A naught V plus minus V negative, right? The V plus technically becomes 0. You make it 0. We earth it. So the formula tend to become what? V naught become V become A naught minus V negative. So the output only dependent to the negative. If negative you give 5 volt, the output will be it's going to be negative, but after multiplying the gain, let's say the gain is 10, so 5 volt output will be how much? Gain is 10, input is 5, so negative 5, so it becomes negative 50, so output will be negative 50. So means what? You see the graph here? The graph is a cos graph. If you give a cos signal in the negative, in the inverting amplifier, the output will be, it invert the input. If input is cos, output will be negative cos. Output will be negative cos. So they invert the signal. Invert the signal to what phase? About 180 phase difference. It will invert. Okay. This is called inverting amplifier. Okay, inverting amplifier. Okay. So in exam, they won't tell you it's inverting or comparator. You should know. How to know? Check. If it's an inverting amplifier, they should have a feedback. The input must be at negative. The input must be at negative. Okay, now another one. The positive we know is 0 volt. You know the P here, the P, the point P there. The point P has a special name. And the point P we call virtual earth. Point P we call it as virtual earth. Virtual. It's not virtual earth. You know, heard of earth, right? Earthing means what is the voltage going to be? This is Earth. This is the real Earth. This is real Earth. 0 volt. Virtual Earth is a point which is not directly connected to the Earth. It's somewhere in the circuit, but the voltage is 0 volt. That's called virtual Earth. Okay. So P is also going to be 0 volt. The P point will have a 0 volt. Why? Okay, this is the reason. In exam, they will ask, what is meant by virtual Earth? 3 marks question. 3 marks question. Okay, what do you have to say? V plus and V plus is 0. V plus is 0 volt. Okay, V plus is 0 volt. To ensure amplifier is not saturated, to prevent saturation, V minus and V plus must be same, must be about the same to prevent saturation. V plus and V minus must be about the same. Okay. So therefore, because V plus is 0, V minus also must be 0 volt. V minus also must be 0 volt. So therefore, V minus also must be 0 volt. So therefore, the P called virtual Earth. Okay, 3 marks. What do you have to say? V plus is 0 volt. To prevent saturation, 1 mark. To prevent saturation, V minus must be same as V plus. Okay. So therefore, V minus also 0 volt called virtual Earth. Okay. Here, 1 mark, 1 point is missing. Please add 1 point. The point missing is the amplifier, the op-amp has huge gain. This is 1 mark missing. In the mark scheme, they give 1 mark for this one. They said V plus is 0. Okay, because op-amp has huge gain, to prevent saturation, V minus must be same as V plus. Therefore, V minus must be 0, called virtual Earth. So please add in your notes. The question asks, what is meant by virtual Earth? First point you must tell, V plus is 0. Second point you tell, op-amp has huge gain, 1 mark. Then you say to avoid saturation, V minus must be same as V plus. Okay, therefore V minus is 0 volt, called virtual Earth. Okay, any question from this slide? Okay, so what you need to know about inverting amplifier? Okay, inverting amplifier has a feedback and the input is at negative. If the signal is cos, output will be negative cos. Amplified lah. The signal will be amplified, but it will be, you will have a phase difference of 180. But amplified lah, definitely. This output is going to be big wave actually. Okay, now the gain for this amplifier is not anymore 10 to the power of 5. So this inverting amplifier, the gain is this formula. This is the formula. The V out or V in formula, negative RF or R in. This is the formula which determines the gain of this amplifier. Okay. Okay, in exam, you need to know how they got this formula. This derivation, you need to know, it's in your syllabus. Derive the gain formula for inverting amplifier is negative RF or R in. 2 or 3 marks question they can ask. So this flow, you should know. Now check how they end up to this gain formula. So the thing is, the I in equals to IF. Okay, what is I in, IF? I in is the input current here. This is the input current. This is I in. The input current is I in. Okay, I in, input current. When you come to the junction P, all the current will flow to resistance up here. This called IF, feedback current. F stands for feedback. Resistance up here called feedback resistor, RF. So I in always same as IF. No current technically moving into the op-amp. No current is flowing into the op-amp. Why? Why no current flowing into the op-amp? Technically, why no current flow into the op-amp? Because op-amp has infinite what? Infinite impedance. It has a very high impedance. Very high impedance means what? Huge resistance. So no current will flow into the op-amp. Technically, all current will flow to IF. So I in is same as IF based on Kirchhoff's first law. Current flow into the junction equals to current leave the junction. So I in equals to IF. Okay, so that's the first line. Okay, now I in. How do you get I in? I in is the potential difference across R in, right? Over the R in. So V in minus 0, potential at P is 0. So V in minus 0 over R in is the I in current, right? V in minus 0 over R in is your I in current. Okay. IF is what? 0 minus output. This output, the 0 to output. So 0 minus output over RF is the IF current, feedback current. Okay. So remember, if your input is positive 5 volt means output definitely going to be negative. So current will flow one way from input I in, then go to IF. So that's why here 0 minus V out, because V out is even smaller than 0. Okay, this is the second line. How they got the first line? I in equals to IF based on Kirchhoff's first law. No current flow into the op-amp because it has a infinite impedance. So all current input flow to the IF. So I in same as IF. So from here, you rearrange, get this feedback gain formula. So gain formula for inverting amplifier is negative RF over R in. So the inverting amplifier inverts the polarity of the output. The V out is pi radian out of phase with the input voltage. The gain formula is negative RF R in. So now the electronic world able to control the gain. Okay, you want to have a lower gain, just change the resistance. The RF or R in determines the gain of this amplifier. Okay, so this is inverting amplifier. Okay, so inverting amplifier. Please, you should know the flow of deriving this formula. Okay, let's go for one example. Yes. So when the input is positive, the output will be negative. When input is negative, output will be positive. If input negative, output positive, current will flow the other way around. Okay, but current flow from RF to RIN or RIN to RF, the RIN and RF is always same. No current flow into the op-amp. So the gain formula for inverting amplifier is negative RF over RIN. Okay, if the input is negative, current flows in the opposite direction, but it's still the same current flowing through the RIN and RF. Okay. Okay, one example. Okay. So in exam, they won't tell you it's an inverting amplifier. You should know, is it an inverting or is a comparator? What feature tells you it's an inverting here? There is a negative feedback. The input is at negative. Okay. During the feedback, the resistance, the first resistance exposed during the feedback is called RF. Here the 22 is RF, 10 is RIN. Okay, now the question is, the circuit shown an inverting amplifier. The question here they tell inverting, but in real exam they won't tell you, so you should know. The input voltage is 0.44. The input here is 0.44 volt. What is the output? So calculate the output. Output is the gain times the input, right? V out is equal to what? Gain times the V plus minus V negative. This is the original formula one. But now gain is how much? Gain something new. Gain is negative RF over RIN. That's the gain formula now. So gain is negative RF over RIN times with the input. Input, we don't have positive anymore. We don't have positive, just negative only. So that 0.44. So negative 22 over 10 times 0.44 It's negative 0.968. So it's going to be negative 0.968. This is your output. The gain times the input, but the gain is negative. Gain is negative. Negative RF over RIN is negative. So 22 over 10 is negative 2.2 is the gain. Means what? Any input here going to magnify 2.2 times but negative. They're going to invert it. Okay. Any questions from here? Okay, we go to the next one. See another one. 10 kilo ohm, 2 kilo ohm. Input is 0.2 volt. The diagram shows an inverting amplifier. Find the gain. Gain is how much? Negative RF over RIN. 10 divided by 2. So the gain is negative 5. Means what? Because RF is greater than RIN, A0 is greater than 1, negative 5. Okay. So 0.2 going to be how much? So 0.2 times negative 5, negative 1. So output will be negative 1. Input 0.2, output will be negative 1. Okay, guys. So this is, I stop here today. This is all. What? This is your, the reason doing feedback. What is negative feedback? Inverting amplifier, new gain formula, this inverting amplifier used for to retain the pattern of the input signal. Music, heartbeat, all be using feedback inverting amplifier, which has a feedback. What is the benefit of doing feedback? You have to know bandwidth increase, less distortion, greater operating stability. Okay, any questions? Okay, guys, so I stop here. This all are something new. Try to look at it again. Okay, you can check in the senior video also. Senior video to get some idea. Then we continue next class tomorrow. Okay, then stop here.